The next speaker is Maarten Koning. He is head of Wind River Technology Office, and Maarten sets the path for the company's technology direction, as well as inspiring, accelerating, and enabling Wind River's customers and employers. Wind River acquired his DSP technology startup in 1997, and Maarten has worked on numerous programs on Wind River, ranging from memory protection, SMP, virtualization, distributed systems, partitioning, ARINC 653, development tools, and RTOS algorithms. And he holds also 14 patents in those areas. And he describes himself as a professional nerd. He has a passion for enabling computers to help humans to stay safe, which is at the moment quite important for all of us. Maarten has an honors Bachelor of Mathematics from the University of Waterloo and a major in computer science and electrical engineering. Maarten, you are going to present us Embedded Systems Go Mainstream, so it fits quite well from the title, and it's yours.
Okay, thank you. That was a great tee up from Mike. Thank you very much, Mike. I think people think we colluded, but I think in reality, you may have programmed me in the past with some kind of a Jedi mind trick that I didn't realize, because these presentations are quite aligned. But before we get to the slides, I want to extend a very warm welcome to everybody joining today. You may have seen IDC's report that by 2025, 30% of the world's data will require real-time processing. Also forecasted by 2025 is that the intelligent edge will be a key driver of digital transformation, with a $700 billion total addressable market. These predictions point to a massive opportunity for real-time data processing within the intelligent edge. Whether you call it the intelligent edge, embedded systems, cyber physical systems, or smart devices, real-time systems are incredibly important to all of us gathered here. And the market research reports tell us that our opportunity space is really growing globally due to digital transformation. So this is a technical presentation, and we'll get to the tech stuff. We're going to talk hypercalls and interrupt response jitter and et cetera shortly. The computer science and getting the bits and bytes right are incredibly important. And normally I would just jump right in, but I want to give a quick update on what's been going at my company, because I suspect similar dynamics are influencing your organizations as well. Most of you know Wind River as an embedded OS company. Wind River is well known for real-time and safety operating systems, our embedded Linux distribution, and also our Wind River cloud platform, which is now powering live 5G infrastructure in the US, something we're very proud of. However, I know many of you have seen the digital transformation messaging and vision on our new website, and that story is bigger than any single product. The larger opportunity is to scale value by leveraging a cloud-connected intelligent systems approach. Just as Mike was talking about, many participants here at the Embedded World conference this week are also on this journey. And together we're finding significant benefits collaborating at the system and cloud level and solution level. We're also finding new engagement from companies and organizations that are coming to the intelligent edge from the IT, cloud, and telecom sectors, as they all look to deploy and operate end-to-end cloud-connected solutions right down to the cyber physical level of sensing, actuating, and processing at the edge. Their diverse use cases are projecting new requirements into the embedded system space, requirements for new protocols, new service deployment mechanisms, such as containers, new middleware, and new expectations of usability, extendability, dependability, and scalability. Traditional embedded systems from decades ago were typically fixed function boxes that were designed, coded, tested, manufactured, and then sold. Now, device manufacturers create edge devices, which are connected devices, as the word edge implies. Edge devices need more than real-time and safety. They must integrate into a broader end-to-end system easily. They need to be managed, often remotely. They need to be secured, and they need to be trusted by those who use them. To achieve this, edge devices need more of the capabilities and core values from the IT, cloud, and telecom space, such as manageability and dependability. This is needed to enable edge devices to better integrate into the broader IT cloud and telecom infrastructure. The traditional development approach of engineering a fixed function, special purpose embedded device is being sanded away before our eyes. More than ever, we need to consider hardware and software flexibility, open APIs, dynamic instantiation of services, so-called service orchestration, self-healing capabilities, stateless replicated data architectures, and more. Gone are the days of doing an out-of-box test, declaring done, and moving on to the next project. The solution, the software, and the deployed device all live on. They evolve even after the product ships. Embedded devices now more than ever feel like the kinds of applications, platforms, and services that IT departments and operations centers manage using hierarchical IT dashboards. So the consequence of these additional requirements is that embedded devices are getting bigger. When we think about the units of granularity for applications and services that are relevant to IT, cloud, and telecom, we see things like containers, VMs, and OS instances that are tailor-made, bespoke, as Mike would say, and instantiated for even just one service or application running right beside other workloads on the same underlying platform. And into this dynamic, remotely managed, general purpose, open, big tech, IT-centric computing paradigm, which is what I refer to as mainstream compute in the title of this talk, we still have to achieve sensing, actuation, real-time, and safety. In the past, embedded system issues were around determinism, resource constraints, silicon enablement, silicon independence, standards compliance, and a rich kernel developer experience. So these core values, they continue to be required at the intelligent edge, but there are new imperatives now, such as developer velocity through open source enablement, developer experience, even using browser-based tooling, managing hardware and software complexity, and enabling system partitioning. Fixed function dedicated systems have now become service delivery platforms that are part of a larger system. As in the Borg from Star Trek, our embedded systems have evolved to be linked together into a hive-like mind that collectively provides a greater value. These additional device-side needs, they motivate a dramatic increase in software and compute. Sometimes the end result can be that the actual software and compute needed for the original purpose of the device ends up being just a small percentage needed by the device overall. To double click on this rising complexity, I'd like to tell you about something a CTO of a medical device company shared with me a couple years ago. He said, we used to build infusion pumps. They were standalone embedded boxes that did what they needed to do, and they were fairly simple. What we build now is an infusion management system that is under the hospital's IT department control and is integrated with the hospital's patient and staff database and its billing system. So at that time, I thought this kind of application-specific system integration was a corner case, a business systems issue, but now I see this is happening in all vertical markets. New, standalone, fixed function, resource-constrained embedded devices are becoming rare. They're being disrupted by edge devices that are resource-rich, multi-core, multi-OS integration platforms, which host a large and diverse amount of software integrated into a bigger solution and a larger value proposition. Let's look at automotive software complexity for a moment. Cars are now software defined. Every software feature requires some amount of compute, bandwidth, and storage. Every feature has to be able to find the others in order to collaborate and coordinate. That in turn requires more software for communication, middleware, high-level services, and frameworks. The numbers being shared within the automotive industry are showing that each decade, there is 10 times the amount of software being integrated into cars. You can bet that all of that software is not running on a single operating system instance, or even on a single OS type. It is partitioned as a collection of applications that run on bespoke OSs that are deployed into one or more integration platforms. And those integration platforms run on complex multi-core SoCs. Automotive is a good use case to consider when discussing software architecture at the intelligent edge, because it is one of the most complex. We might be tempted to say, if software can fly a plane, of course it can drive a car. but the modern autonomous car is way more complex. Not only do cars have to safely navigate a dynamic environment without the help of pre-reserved space around it as planes enjoy, the time frame for decision correction is much tighter for cars. The feature set in a car is so huge and the amount of software so large that car manufacturers need to divide and conquer to make their model year release dates, even for cars that don't offer fully autonomous driving. To do this, they specify and receive software applications from tier 1 suppliers that they can include and run on their in-vehicle integration platforms. For software applications that are contracted out, automotive OEMs calculate and provision a compute budget that their suppliers have to deliver within. Those limits can be enforced in the car by running each application in its own partition, separate from other applications. Each of those partitions can be given a slice of compute from the overall multi-core SoC, and they can be engineered so that the total fits. And if those partitions are fault containers, then when a fault occurs in one, it can be determined whose fault it literally is. The automotive industry understands the value of this. They've been doing the same thing for years with hardware for ECU modules. And now, due to the increase of software in their complex product, they've had to pursue an integration platform approach even sooner than other vertical markets. However, this integration platform design pattern is coming horizontally to intelligent edge devices in all vertical markets because traditional embedded systems are evolving into connected, IT-managed, multi-service intelligent edge devices, increasingly powered by complex multi-core SoCs. So what does this mean for system architecture? Well, every good software architect knows that their software architecture needs to be flexible because it enables product managers to reimagine the product every release or even during a project, right? Some success factors that you can consider when evaluating your next software architecture are the degree to which it isolates software elements from hardware and also from other software elements. Also the degree that it enables those separated elements to easily collaborate and share data and system resources. CI/CD is also worth calling out here, since some elements have to be updated frequently, while at the same time, other elements in the system are stable and should remain so without unnecessary updates during CI/CD. Partitioning software into appropriate granularity decouples software, and that reduces the amount of testing and service outage that occurs during CI/CD cycles. So let's look at how an integration platform like this can be assembled on a modern multi-core processor in a way that lets it run diverse workloads. When there are safety workloads mixed in with non-safety workloads, we call that system a mixed criticality system. If those workloads share hardware and there are potential fault propagation paths from the non-safety software to the safety workload, we need to partition the system in a way that protects the safety workloads from being impacted when such faults occur. A safety certifiable hypervisor is one way to do that. Another way is to run the safety workload on a distinct computer, which is sometimes called a compute island. A compute island is dedicated safety hardware separate from the general purpose compute. This compute island approach is something that NXP, Xilinx, Texas Instruments, Renesas, and others offer today. For multiple reasons, it is also increasingly common to see Linux in these mixed criticality systems. A big one is that over the last 20 years, open source has pretty much become Linux-based open source above the OS level. And now board and silicon vendors only provide board support packages and device drivers for Linux, not for other operating systems. This means that Linux is always the first operating system available on new hardware. Also, because these boards and SoCs are now so complex with GPUs, NPUs, and other accelerators, the drivers for those coprocessors and also for other peripherals don't get implemented for other operating systems. Finally, Linux has excellent support for containers and VMs, and that makes it a good choice for all those general purpose applications that intelligent edge devices must now run. Let's explore some options that enable real-time and safety while still allowing Linux to be in the system. This slide shows 4 distinct scenarios that enable Linux and real-time to be combined in the same multi-core SoC. First, the first one, number 1 there, that's core isolation. This is where Linux allocates an entire core to a single application and that it ensures that the core is not disturbed. This means interrupts won't be handled on that core and other processes won't be scheduled on that core. By dedicating the core to that one process, it is possible to arrange that 100% of the instructions running on that isolated core come from that one user level process. This allows us to engineer it to perform a real-time function. The problem with user level core isolation for real-time is that sooner or later that process is going to want to make a system call. And when it does, it'll be off executing potentially non-deterministic code paths in the Linux kernel, perhaps even contending for locks with processes running on other cores. So an alternative to that, we're still on option 1 here, is to leverage virtualization on that same core and combine an RTOS with the application so that when it needs to call an OS, it calls the RTOS. And the RTOS handles the request deterministically, and that avoids the Linux system call path. The de facto Linux hypervisor, KVM, can be used to set this up. This configuration provides respectable soft real-time numbers. This gets us farther towards a rich real-time programming environment with Linux. However, the virtualized RTOS itself sometimes needs to do things that the virtualization hardware cannot allow it to do, such as acknowledge an interrupt in a virtualized interrupt controller. And then the hypervisor must be invoked to handle it. When the RTOS makes a hypercall like that or triggers an exception that the hypervisor has to handle, that kicks off a code path known as a VM exit, which in this case runs in the underlying Linux kernel, again, potentially introducing non-determinism. Granted, these VM exits are typically less frequent and more manageable than what occurs for user level processes. But when it makes system calls directly to Linux, and it will, it's difficult to put an upper bound to the execution time of the VM exit code path. Hard real-time systems worry about the worst case timing, not the average case timing or the typical case timing. And for this reason, we consider this core isolation scenario that has Linux running on all the cores, a soft real-time scenario. Scenario 2 is interesting in that it still has Linux potentially booting on all the cores, but Linux has this CPU hot plug interface. And with that, we can take away one or more of the cores for the real-time workloads dynamically. And when those real-time workloads complete, you can even give the CPU back to Linux. This can be done also statically by reserving cores for real-time workloads at boot time. Core offload's not a new approach, and it used to be called unsupervised AMP. The problem with unsupervised AMP is that wayward code in the real-time workload can crash the Linux kernel and vice versa. Nowadays, processors support virtualization, which enables this scenario to be more viable than in the past. What you can do now is first run a small real-time capable hypervisor under the real-time workload, and that can ensure that there's no fault propagation from that core to the Linux kernel. One issue with this scenario is that until we collectively achieve some level of safety cert with a Linux kernel, we still can't trust this approach for safety workloads because the Linux kernel can still interfere with the offloaded core. So this scenario is really only appropriate for non-safety real-time workloads. Scenario 3 introduces the possibility for safety workloads. And the hypervisor running underneath all of the cores is safety certifiable. It can protect the safety workload from non-safety workloads. This has sometimes been called supervised AMP, and such systems feel a lot like a distributed system that is running inside the SoC because each guest runtime has its own full life cycle that's independent from the other guests. This is the primary method today for combining Linux with real-time and or safety workloads on the same CPU cluster. And there are commercial products on the market, including from Wind River, that do this. Finally, there's scenario 4, where the real-time or safety workload is run independently on its own compute island. For heterogeneous multi-core SoCs, the compute island is in the same chip as the general purpose CPU cluster that runs Linux beside it. In this case, no hypervisor is needed underneath Linux, and Linux can manage all the general purpose cores as they are independent of the real-time or safety workload. There might still be other reasons to run a hypervisor if you have other OS types, but if it's Linux on the general purpose CPU core, then cluster, then you don't. This slide's a bit of an eye chart, probably best reviewed offline in the interest of time. It does help us see the differences in the scenarios that I just went through as it illuminates the places where there is non-determinism. The red, I'll just go back here for a sec. The red lightning bolts, those are system calls to Linux, and the yellow lightning bolts are non-deterministic VM exits to KVM. And for all 4 scenarios, you can see what runs at the user level and at the virtual kernel level and the physical kernel level. Another aspect you can really see in this diagram is that the real-time and safety devices, which are shown as these little gray robot arms, are mapped right into the RSL kernel, and the RSL device drivers access these devices directly. The key to this kind of real-time service for Linux architecture is that it requires that real-time and safety software is the only software between the real-time or safety applications and the hardware that it needs. Once an RSL runtime is activated, it needs a way to use resources from Linux, and it needs a way to collaborate with services or applications residing on Linux. Virtio is ideally suited for this, and something that is actively being pursued in the industry to create systems like this. In an RSL system, the Virtio path from an RSL runtime can go down to the hypervisor if there is one, but it can also be horizontal and go across to Linux if there isn't a hypervisor. This is where the term hypervisorless Virtio comes in, which some of you may have been experimenting with or have heard about. With hypervisorless Virtio, the Virtio transport is via shared memory and terminates in a daemon process outside of RSL, usually a Linux process. The daemon process, the proxy for the RSL runtime, and it can read or write files on behalf of RSL using Virtio 9p, or it can connect a console to the Linux pseudo terminal, to a Linux pseudo terminal, and it can integrate the runtime with Linux networking, IPC, and other services. From an RSL applications perspective, it sees the same underlying runtime service, regardless of which of the four scenarios is underneath. Let's have a look at a real-time use case where we have an industrial computer with an application that uses time-sensitive networking. It's a typical M2M use case. You might want separation because there's an operator running one computer and the device is doing something dangerous. So it's elsewhere, maybe in a different room or behind a barrier. But you still want to have super low latency connectivity. And so time-sensitive networking is really helpful for that. The problem is, though, that you might have jitter issues. Well, there are jitter issues to using Linux, even with preempt RT patches. So having an auxiliary runtime that has real-time core values and can run the TSN stack, network stack, and maybe OPC UA and the TSN application with dedicated hardware. Basically, it's in a little embedded system inside the general purpose compute engine that's running Linux. That architecture can solve this problem, whether it's the scenario one, whether it's the scenario two that we talked about, where you have a core offload, or it's partitioning with a hypervisor, or it's compute island. The architecture is the same, to take an auxiliary runtime and offload the real-time, the hard real-time or safety service from Linux. Okay. All four scenarios look the same to the application from a system architecture perspective. Developers can approach their application programming tasks in the same way. There's always Linux available for the large amounts of non-real-time, non-safety code. And that's really important for the reasons mentioned in the opening keynote, that there's a developer journey that often starts with a one-click download at the beginning of a project to start with Linux. So a Linux first, Linux-centric approach is highly relevant to the way that people are innovating and developers are achieving high velocity today. And the RSL workload, regardless, can run on a variety of platforms because it might not be apparent later on, or early on, I should say, which end platform would be selected. So whether it's hypervisors, heterogeneous multi-core, discrete processors, and all of these configurations could apply. With this architecture, there's a significant amount of software and services that are able to stay off the RSL runtime and enjoy the easier open source compatible Linux environment, such as monitoring and reporting software, system management, file systems, and removable media, HMI, internet connectivity and firewall, wireless connectivity, and software packaging and update technologies. The reason this is advantageous for intelligent edge device manufacturers is because of system flexibility, the availability of drivers and BSPs, rich options for high-level software compatibility, and separation of concerns in the system architecture, and that's a good thing. By pursuing an RSL-like architecture, runtimes can be best at what they were designed to be, whether a general purpose OS, a real-time OS, or a safety OS. This relieves the tension that occurs at the implementation level when there are conflicting core values. Since with RSL, with this kind of auxiliary runtime architecture, the core values can be different between those three types of OSs. I believe this kind of system architecture will improve developer velocity, reduce time to market for complex systems, including mixed criticality systems, enable IT/OT convergence to accelerate and enable greater reuse of software across product variants and projects, and is also highly aligned as Linux continues to get better at real time with the evolution of the Linux kernel itself. Ultimately, intelligent edge devices will be able to be deployed, developed, deployed, operated, and optimized faster, better, cheaper with this kind of an architecture. And this sort of flexibility is increasingly needed due to all the requirements that are being projected down from the IT, cloud, and telecom space. Thank you.
So, thank you very much, Maarten. We have, due to some technical synchronization issues, a short break, a very short break, and then we come to our final presentation.